Hi, welcome to the video on question 8 of your nuclear chemistry review. Question 8 asks which nuclear reaction is not balanced, and the correct answer is B. I'm going to explain why it's B. So remember, in order for a nuclear reaction to be balanced, you need the total mass number on both sides of the reaction arrow and the total atomic number on both sides of the reaction arrow to be the same. They need to be equal. So let's go ahead and check equation 1 and prove that it is balanced. So on the reactant side of the reaction arrow, to the left side, there's only one reactant. So of course the total mass number, remember the mass number is the number on top, is just going to be 14. And then the total atomic number is just going to be the 6. Okay? So we have 14 and 6 on the left side. Let's check to make sure that the right side, when we add up the mass numbers and atomic numbers, also give us the same value. So we add 14 plus 0, that gives us 14, and then 7 plus -1, which is the same as -1, so that gives us 6. So as you can see here, both the the mass numbers and the atomic numbers are equal on both sides. B is not balanced. We're going to come back to that and I'll explain why B is not balanced. Let's go on to the next one. So the next reaction, we have a neutron and uranium on the reactant side, and on the product side we have several things. So let's go ahead and add it up and see if the atomic numbers and total mass numbers are the same. Starting with the mass numbers, 1 plus 235, we get a total of 236 on the reactant side for the mass number, and then for the atomic number, 0 plus 92 gives us 92 for the atomic number, total atomic number on the reactant side. Now let's go ahead and check on the product side. So on the product side, we have all of these values to add up, but the other thing we need to keep track of is that we have this coefficient of 3. This coefficient of 3, just like in math, means it's telling us we have 3 neutrons. Remember, this is a neutron. And so we have 3 of them. So when I add up my mass and atomic numbers on this side, I need to be cautious of that. And one way that we can do that is just by distributing whatever the coefficient is, so that 3 to the mass and atomic number of the species this coefficient is in front of. All right, so let's go ahead and do the tally here. So if I were to tally up the total mass number, I would add 141 to 141 plus 92 plus 3 times 1, which is just 3. Because remember, I have that coefficient, I've got to make sure I distribute that. So the total mass number I get here is 236. And again, I did 141 plus 92 plus 3 times 1, which is just 3. So 141 plus 92 plus 3 gives me 236. And that matches what I had on the reactant side. All right, let's check the total atomic number. So we have 56 plus 36 plus 3 times 0, which is just 0. So the math I would do here is 56 plus 36. And that gives me 92. And so when I check that out, 236, 236, 92, 92, boom, boom. Looks good. All right, the last one here is pretty simple, and that's because we have a gamma decay. So remember, with a gamma particle has no mass and it has no charge. When it comes to particles, the top number represents the mass, and then the bottom number represents the charge. When you're dealing with an element, something you find on the periodic table, the top number is the mass number. So both are kind of about the same thing, like both describe the mass of the species. And then the bottom number is your atomic number, which is the number of protons. But if you're dealing with a particle, this represents the charge of the particle. Okay, so if we check this out, we see on the reactant side we have 60 and 28. That's our total mass and atomic number respectively. And then on the product side we have 60 plus 0, which is just 60, and then 28 plus 0, which is just 28. And so we can see again that that's balanced. Now the one thing I want to point out for gamma decay, the reason why we have this star or asterisk here in a gamma decay, notice that the parent isotope, which is your reactant, what you're starting with, is the same element and the same isotope as your daughter isotope, the product that you make. So in order to distinguish that, we use this asterisk to show that our parent isotope is unstable. And essentially what happens in a gamma decay is that energy, that extra energy that this nucleus has, is released as a gamma particle, which is just a photon of light with energy corresponding in the gamma range. All right, now let's come back up to here and prove why this one is not balanced. And I'm going to make this look a little bit more clear. This is a hydrogen, by the way. Okay, so let's go ahead and check this one out and show that it's not balanced. So once again, I want to do my total mass number and atomic number on both sides. Let's start with the reactant side, 14 plus 18. And that gives me 32, I'm pretty sure. Let me just double check. Is that 32? Oh yeah, I can do maths. Okay, so the total mass number is 32. Now let's do the total atomic number here. And because I ran out of room, I'm just putting it above and below. Total atomic number 8 plus 9, so that's 17. All right, so let's check to see what we have on the product side here. Now once again, we have a coefficient, so we need to make sure we sort of distribute that out, because that coefficient is telling us we have 2 hydrogen 2 at nuclei. So starting with the total mass number, we would do 28 plus 2 times 2, which is 4. So this is 28 plus 4, and that equals 32. So far it's looking good. The mass numbers are adding up. Now let's do the atomic numbers. We have 14 plus 2 times 1, which is just 2, and that gives you 16. So that's where we're messed up there. The atomic numbers are not the same. You have 17 on the reactant side and 16 on the product side. So that explains why this one's not balanced. All right, I hope you found this video helpful. Have a quality day.